Hi everyone, my name is Anjian Chen, and today I'm going to present on my final project on retinal vessel detection. Here's the outline of my project. I want to go over a type of biometrics that wasn't covered in depth during lectures, retina. This project is referred to the study of Peng-Yu Tang. The data used in the project is described in the study conducted by Adam Hoover, Valentina Konetsova, and Anne Goldbaum on locating blood vessels in retinal images by piecewise threshold probing of a matched filter response. Database contained 20 retinal images, 20 hand-labeled vessel networks provided by Adam Hoover, 20 hand-labeled vessel networks provided by Valentina Konetsova, and 20 sample result labels produced by their study. Here is a sample of the retinal images from the database. And here are the sample retinal vessel labels from the database. As you can see, there lie slight differences between these labels, as I'm going to pair them with the same set of retinal images and compare the performance and their mean AUC. Before an experiment, we need to do some data preprocessing. Since all the images and labels described above are packaged in a tar file archive file containing gunzip compressed portable pixmap format images. To do data preprocessing, first we used MATLAB on tar function to extract all files in the archives and organize them in different directories. In each directory, loop through each file, unzip the file using gunzip function, extract the name of the file, and resize the image for training. Specifically for the directory containing RGB retinal vessel images, these images need also be converted to grayscale. Lastly, save the files in .tif format for later retinal vessel detection. The main experiment process starts by loading the image from the data directories using the same retina images but pairing with different labels to compare the main AUC. Then extract the features from the training image, perform multiple Gabor transforms, normalize the transform image, append the transform image to features, and use this output features to feed into a generalized linear model. Perform pseudo cross-validation since only the top half of the image is used for training and the bottom half of the image is used for testing. Calculate the sensitivity and specificity by thresholding the output of GLMC test and comparing the threshold image with the bottom half of the label. Lastly, plot the result ROC curve and append the computed AUC to compare the performance when paired with different label directories. So let's start with the small demonstration which I achieved the best result of the highest AUC. Let's start by running the code. As you can see here, I'm applying multiple Gabor transform to the testing image. And here's the result. On the top here, we have the original image comparing with the output of the GLM and the optimally thresholded output from the GLM. On the bottom, we have the testing image, the original retina vessel image, and the provided label with the output of the GLM. The compared results are plotted on the left side here with the ROC curve having AUC of 0.9. However, the mean AUC of the entire dataset are 0.6656, 0.7560, and 0.7732 respectively, which only means moderate performance. To improve the performance, we can either enhance Gabor feature extraction using multiple scales and window-based features, including a window of neighboring pixels responses to capture local texture context instead of just the Gabor response at one pixel, or improve GLM structure, adding additional features such as intensity and gradient magnitude from the original image, histogram equalization or contrast enhanced version of the image, and morphological features or switching link function. Additionally, we can also do data augmentation, applying slight rotation, flips, or translation to the training images to increase robustness and perform cross-validation across multiple images rather than patches from the same one to ensure generalization. Here's a reference of my project, and thank you for your attention.